In this video, I'm going to do a fairly quick rundown of the Copeland textbook as it relates to Chapter 4 of the HSC Engineering Studies course, which is dedicated to telecommunications. Now, already by this stage, with the class that I'm teaching, we've already had a look at the syllabus, we've already had a quick look through the whole chapter, and we have a pretty good idea. And also, I've already posted all of the work on Google Classroom. What we're going to do now is we're just going to talk through what is in these pages and what are some of the things that I think you should focus on. I'm not going to read everything, but I'm going to give you some of my perspectives on a few of these things. So, the first thing is that we always remember that each of the 4 chapters is divided up into what I like to call the profession, materials, mechanics, and then communication. Now, in this exam, as we're getting ready for the trial examination, the trial HSC, I'm not going to go through everything in excruciating detail yet, so I'm just going to focus on the things that are important, I think, as I see that for the exam. So communication, I don't think there's a lot in this chapter without scrolling all the way down. So there is a lot on the scope of profession and the history of the profession, so let's focus on that first. So it says the nature and scope of telecommunications engineering. It says that, well, always when we talk about engineers, they're responsible for design and development, or I'd say production, or development's a good word, for telecommunications equipment and infrastructure. So they modify designs, they're responsible for developing equipment, and this includes telephones, satellites, televisions, and radio networks. That's a pretty reasonable rundown. The thing that I always like to point out is that my experience with telecommunications comes from signaling engineering, and signal engineers are the people who work on railways, that they do the lights on sticks. So signaling is a really important part of railways. We used to call it the dark art because no one really understands how signaling works, and compared to civil engineers who just dig holes. Whereas if you wanted to not be respectful and not call them the dark art, then instead you call it lights on sticks, because that's all they did, is they just put lights, traffic lights on sticks. The thing is, though, they not only are in charge of the lights on sticks, they're also in charge, like the traffic lights for trains, they're also in charge of the switches, the points motors, and so while I say this, I'm doing a hand gesture of the trains as the train track shifts so that the trains can go different spots. So we have crossovers and we have turnouts, and I could look that up, but I'm a little bit lazy at the moment, so you guys can look up crossovers and turnouts on your own computers. That's a fairly important part of telecommunications. There's also would be some degree of telecommunications that's involved in all of the traffic lights in metro areas like Sydney. And the reason I say that's just that I've worked in rail, so that's what I'm familiar with. But I know it's a very hard, or at least it was 10 years ago, it was very hard to find signal engineers. They were in high demand. So if you go into telecommunications, it would be something I would consider looking into. So that's the big thing. But when we looked at the start of the course, we looked at different fields of telecommunications. Different fields of engineering. Telecommunications falls within ITEE, which is Information and Technology, Electronics and Electrical Engineers. So it falls into that same sort of ballpark, but there are some specific things that we're going to learn about that really relate to telecommunications. So with OH&S, well, there's risks in any job that, for instance, just when you're digging up the trenches that you're going to put these telecommunications cables in, for example, you could fall into them, you could hurt your ankle. That's an example of just the risks that are present in pretty much any field of engineering. But there are some specific ones that we want to look at as being a greater risk, and that is that you can work with fairly high strength broadcast frequencies. Not high frequencies, but there is concern about the effects of being too close to radio transmitters, as an example. I have heard various points of view on this. I don't want to quote anyone specifically, but I had a boss who said that when he worked, he was at one point, he was a civil engineer, but he was working on the infrastructure to put up satellite dishes for distribution networks. And yeah, he was concerned about, like, there are stickers that he had to peel off that say, you know, this emits high amounts of, I don't want to say radiation, but it is by definition radiation. And my accordion teacher, again, I don't want to, you know, call anyone out, but he did say that, yeah, he was concerned that perhaps there could be some risks to the, you know, I'm probably not going to use this recording, so it doesn't really matter. Okay, so that's probably the biggest thing I would consider. Yeah, dangers of falling equipment, lightning strikes, electrical hazards. I mean, they seem like pretty standard sort of things. Okay, moving on. Training for the profession, well, like most things, they recommend you do 2-unit maths, what we call advanced maths now. Physics, chemistry, engineering studies are probably the best subjects to do. Maybe things like IPT and software design could be useful. Probably IPT might be more useful than software design, but, you know. Yeah, often it will have an overlap with the first 2 years with electrical and electronics engineering. Okay, career prospects. So large companies such as Telstra, Optus are actively looking to expand. Yeah, I just reiterate that I think rail is fairly important. Relationship to the community. It is interesting, right? I would say it's not good, not great. Sorry, not terrible, but it's not great. So definitely with the rollout of 5G, that there was a lot of concerns about 5G. So you heard about in some countries where 5G towers were getting destroyed, that places like India had a lot of concerns about the 5G being the cause for their high COVID numbers, except for the fact that India doesn't have 5G. So that's where, you know, there's a lot of misinformation. So radiation from satellite transmission and to mobile phones has led to community fears about cancer, especially young children exposed to it. Now, I am not a specialist in this, so I don't really want to go into too much detail here, but I'm glad that Copeland acknowledges that this is a community concern. When people talk about radiation, the thing that I'm led to believe is that when it's ionizing radiation, that's when you need to worry. Ionizing radiation is where it actually knocks the electrons off your atoms. Yeah, that's what ionizing means. Yeah, it strips the electrons. So UV light, right? So we all, every day, we go and walk around underneath a great big source of radiation, right, that is ionizing, right? It emits UV light, that ionizing radiation. We call it the sun, right? And we have to accept that the sun exists, right? Some people would like to ban the sun because it, you know, does cause cancer. It's well known that it causes cancer, but it's pretty important for our society. And so we all we have to put it within a broader context of, you know, at the moment it's 10 degrees in our classroom and we consider that really, really cold, but, you know, it's all relative because we're used to having fairly mild winters. Okay. Technology is unique to the profession. Well, telecommunications is heavily dependent on semiconductors. So that's a pretty important technology that's only really in telecommunications. Satellite technology is also another factor that I would say there's a pretty strong overlap with aeronautical engineering there, because often the people who launch rockets are aerospace engineers. So that's another technology that we consider. Optical fiber is also, I mean, it is used in biomedical applications, but it's pretty close to being unique to this profession. As for legal and ethical implications, the book says see chapter 3. I've already highlighted quite a few of them. So the one that I like to draw on is what we call NIMBYs, not in my backyard. So everyone wants to have good phone reception, but nobody wants to have the transmitter attached to their house. So NIMBY is not in my backyard, and that's a real concern that's a real problem that we have to deal with telecommunications, is public support for having radio transmitters. Not everyone wants to have radio transmitters near their house. There's also a lot of concerns with things like legal and ethical implications of monopolies. So in America, I've already mentioned to you guys that in America, there are cities where there's only one internet provider. So like it might be Comcast, for instance. Comcast, if you're ever on the internet, it's not a well-liked company because, look, there's a scene in The Simpsons there we go, where Homer is upset with Moe. Homer is upset with Moe, and he goes and tells Moe, and he says, hey Moe, you just lost yourself a customer. And Moe's like, I'm sorry, I can't hear you, because he's got so many customers, right? So if you're someone like Comcast, there's many industries have what they call the 80-20 rule. So the idea of the 80-20 rule is that 20% of your business, right, 20% of the people in your company, of your customers, will generate 80% of your there you go. They will generate 80% of your income. So in that situation, when these people start saying, hey, I'm unhappy, you can ignore them because they don't make you very much money. The people who you need to keep happy are those people, right? So when but what you do hear is a lot of people whinging on the internet saying, my internet doesn't work, because it's like they expect internet to be like, a human right or something like that. It's almost like they feel as though if you don't have the internet, it's like you're somehow disadvantaged. Yeah. And so this is, in case people didn't get that was being sarcastic, right? Because, internet's pretty important, especially in, say, education, right? That if you don't have the internet, it's pretty hard to compete. So anyway, there are a couple of key legal and ethical implications. There's others which we could go into, but they start to get into things like, they become more about like artificial intelligence or monopolies on large telecommunication services like Google, Facebook, and Apple, especially Google and Facebook, because they're software companies. So what they do with the internet is fairly important. Like how much data can they keep, whether or not they have a responsibility to censor content, whether or not these things can be misused for, say, election, interfering with elections, right? So these are all implications that relate to telecommunications. But we're starting to get into more social interactions there rather than our real hard engineering. But there's lots there, and I've highlighted 3 or 4 that I think are pretty deep already. So, okay, moving on. Engineers as managers. So when they say developing, I would also say that it's not just designing and improving on those technologies, but also the implementation and the maintenance of these, the operation of these infrastructures is really important. So engineers in all fields, they have to not only manage the design, but they have to manage the operation of these things to make sure that they're working as intended, that they're working safely, that they're making a profit for whoever is the owner of that asset. So it might be for the state government, they don't want to necessarily make a profit, but they want to keep their budgets down as low as possible. A big one that's really interesting is the NBN. Now the NBN is kind of, a decade, it took a decade to produce this infrastructure, and that's a legal and ethical consideration about whether or not the choices made by those who implemented the system, whether or not we wasted money, whether or not we deliberately chose substandard choices for choices for the infrastructure that were saved money over the course of maybe 5 years, but they were definitely more expensive over the course of decades. Okay, so that's some considerations there as managers. Okay, current projects and innovations. Now, I always find these tough because even if you have the most recent version of the textbook, so we're waiting on a new version of this textbook to be released this year. I think the version we have now is, I can't remember, I think it's 8 years old, something like that. at the time 3G was a new innovation, and you could even say GPS, right? In 2013, not the idea of everyone having a GPS device in their phone was still a relatively new one, whereas you guys probably can't really remember a time when everyone didn't have a phone, and that is an interesting consideration. So, for instance, we have people who are worried that the COVID vaccine is going to put some sort of tracking device in them, whereas everyone is okay with the idea that they carry around a tracking device in their pocket everywhere they go all the time, and that they have a listening device that can be switched on remotely by the government without you having anything to do with it. You can't even take out the battery. You used to be able to take out the battery and know that, well, okay, the government can't put in the battery, right? Whereas now you can't remove the battery. So Edward Snowden, the famous whistleblower who talks about how telecommunications networks were being used by the US government to spy on pretty much everybody. He now lives in Russia, and he talks about he opens up his phone when he gets it. He removes the microphone from his phone. He uses a soldering iron to actually remove the component that is the microphone, which is why whenever you see him being interviewed, he's always wearing headphones. So, sure, they could. So there you go. He's got his headphone. But yeah, typically he's wearing headphones in his interviews. Maybe that's why he doesn't like the Apple ones. Maybe they're more of a concern. Anyway, something I've been thinking is really interesting. I posted onto. I have like a Facebook group that I just put like whenever I find interesting technologies. How am I going to get to that? Here we go. So this was the old scandium, and I now call it ecoboron, which was the first name of scandium before they discovered scandium. So yeah, let's see. Anyway, and one that I thought was really interesting was implants, and what people are looking at now is... Did I not include that? This is interesting, but what I was looking at... Here we go. Implantable... There we go. So you can get NFT tags that you can inject under your skin. Well, so you know how you can use your phone to pay, like, to tap and go? Yeah, so that's just reading an NFT tag. Yeah? And so he's got an implant that he just uses his finger. He's got it in his finger? Because usually you put it like more into the meaty part of your hand. That's cool. Okay, so it's in his finger. So it's about the size of a grain of sand. And yeah, you can inject it into your body. So this is the US prices. It's more than double once you order it to Australia. And so what you can do is you can this is people who are working on. They want to make it so that you can get into their car, right? So that it unlocks their car. I was looking at that. I thought that was an interesting idea. So you can have just NFC tags that you can put into your finger. So I think it was Sweden or Switzerland. I always do get those countries mixed up, but there was some security company, and they were allowing their staff members to use implants rather than having to carry around a card or a badge. So the idea is that it's pretty hard. You're gonna know if you lose your implant, right? Whereas if you get your card stolen out of your wallet, you might not know straight away. Whereas if someone holds you down and then forcibly takes your implant out of your finger, you're probably going to know that you've been compromised. So that I thought was a pretty new interesting technology. So yeah, we've talked about 5G. We've talked about Starlink is a new technology. So Starlink is an Elon Musk project is probably the word. So that is using satellites to provide internet pretty much everywhere. And that could really work well to undercut places like... so I remember sitting on a plane with someone from Minnesota, and they were telling me that Comcast is the only option. There's just no other alternative for. Whereas in Australia, there's multiple internet providers, and that competition helps to keep things balanced. Whereas Starlink, because it doesn't require any physical infrastructure on the ground, it's all on the satellites. It could really undercut places that don't have very competitive internet options. So that's an interesting consideration. Okay, so now we're going to look at the history of the telephone and its impact on society. So the telephone and its history. So where do we want to go with? So first of all, we have Samuel Morse developed a way that you could send electrical signals down a cable. So initially, the trying to look for the very first telegraphs. What they would do is they were attached to a pen, and when the electrical signal came through, the electromagnet would draw the pen closer, and it's probably this sort of thing here. Yeah, so it would draw the pen closer. I'm trying to find these. But very quickly, people found that they didn't actually need to do this, that they could just, the operators could say that without having to read the piece of paper, without having to read the transcript, they could just hear what was being written by the sound. They just recognized the scratching of the paper. And once they could recognize the scratching of the paper, they said, well, okay, we're not going to worry about the paper anymore. We're just going to have people who transcribe it in real time. And so it took some effort to be able to use this. So my father-in-law, when he lived in the Czech Republic, I believe, he wanted to get a radio operator's license because it was a thing to do before the internet. And what he would do is, he said that in order to get the operator's license, you had to learn to send. You had to be able to learn to send. You had to pass a Morse code test, and he could only get to, I think, 5 words a minute. I think that there was, maybe the requirement was 10 words a minute, and he really struggled to get faster than that. But I'm just trying to look. I think it's unfortunate I can't find the paper again. I'm probably not going to use this anyway. But yeah, I think you get the idea. Maybe next time if I record this, I'll try and have the pictures set up first. Maybe, probably not. Okay, so obviously the Morse code we saw in the video is pretty significant. It was the first time people could send messages in real time over long distances quickly. And when we talk about quickly, like almost instantaneously. So this was really important. We talk about the impacts of this, that wars that were fought that could have ended sooner if someone could have passed them a telegram. There's a movie which, when I was a kid, was still relatively well known, but people probably haven't heard of it anymore. I'll be interested to tell me. You'll tell me if you've heard this. Okay, so in this movie Gallipoli, look, this movie's from 1981, right? It's not going to be a spoiler if I give a spoiler for a movie that's literally 40 years old. They get a message to say that we don't need to attack, and they have runners, right? Kind of like how we have our Year 8 messengers, right? And this guy, his job is he has to tell the guy on the front line that he has to pass on the message. The problem is there were 2 runners, right? Two guys who were best mates. They used to race against each other before World War One, and the problem is that they sent the slightly slower runner because he felt bad for him. So he's like, okay, the slightly slower runner, Mel Gibson, he's the one who delivers the message, and he gets there like, so this is the guy as the faster runner, right? And he's going to go over the top, and that video that everyone's seen in the Shire, the over-the-top video. Anyway, so this is Mel Gibson running to get the message, right? And then the fast runner, the gold medalist, he's getting ready, and how do you think this movie ends? Pow, pow, pow. Okay, yeah. Right. So this is an example of fast communication. Can. Well, yeah, definitely can save lives. I mean, I've even taken out war where it's like, well, people. There's a good argument to say that Australians shouldn't have been in Gallipoli in the first place, but absolutely, telecommunications have a huge impact on being able to communicate with the fire department. Yeah, to be able to send a message quickly so that people can provide help would be an easy example of how telecommunications could save lives. But it also has an impact on things like the stock market, right? So these days, microseconds matter in the stock market, and telecommunications definitely play a part in those people who have those microseconds of advantage can make a lot of money out of it. Okay. There was a cable run between the English Channel, and then they're talking about messages that would have taken weeks could now be received the same day. Okay, then the next thing we're going to focus on is the telephone. So Alexander Graham Bell, I happened to see some documentary or some Lifetime movie about Alexander Graham Bell when I was a kid, and the thing was that he and his dad both tried to teach the deaf to speak, right? So I'm sure at some point you've seen people who are deaf who speak, right? And they speak with sort of an accent because it's hard to address some of the finer points of language without being able to hear to contrast. And so there's this thing called the International Phonetic Alphabet. Okay, so the International Phonetic Alphabet is this thing. So before the International Phonetic Alphabet, Bell had a different. He had a different one. Let's see if we can find phonetic notation, maybe, and then. We could. Okay, so Alexander Melville Bell, right? So that's Graham. This is his dad, right? He developed one of the first international phonetic alphabets, and his were all based on where the tongue should be, right? And so that was to try and teach deaf people how to speak. Yeah. You get used to it if you look at linguistics. You do get used to it. But eventually they wanted to have something that was a little bit more easier to type in the typewriter for starters. Anyway, so what Bell had hoped to do was he hoped that he would be able to use these the oscillation, right, the oscilloscope of the so when you see so that when people talk and they talk into a microphone, that they see the waves moving up and down. What I really wanted was one for speech. Anyway, the point is that Bell quickly realized that you couldn't actually tell with speech. Right, that it just moved too quickly, and you couldn't actually see the letter B, unfortunately. But what he did find is that, hey, but you could actually send this message across the room. And we saw in the video that even a decade after the development of the phone, there was only a dozen people in Washington, D.C. who thought that a phone was a worthwhile thing to own, because people thought that Telegram was fast enough and good enough. So why would we need to be able to talk to people in real time? But believe it or not, other people eventually, when they heard it, they're like, "Hey, this is actually a really good technology," and eventually people did adopt it. Okay, so Thomas Edison, right, who gets a lot of hate, was a pretty prolific inventor, right, boys? Right, gets a lot of hate because of his current war with Tesla, but he also worked on the first gramophone. So he used wax cylinders to record speech, and so the idea is that by talking into a gramophone, it would create a vibration. That vibration could be connected to a needle. That needle could leave an indentation on wax, and then when you reverse the process, the needle running on wax could vibrate a diaphragm, and it would produce something that sounded like the sound that created that vibration, which is pretty clever, right? Eventually, people stopped using wax cylinders and started using vinyl discs, and that's where we get to the records that we know today. Thomas Edison was also pretty keen on the camera. He didn't invent the camera. The Frères Lumière, the Lumière brothers, which the university I went to in Lyon was named after the Lumière brothers. They were the first people to develop the camera, and they started making movies. Whereas Edison, he was sort of the person who really popularized cameras in America. And the reason why Hollywood is where it is it's basically as far away as Edison as they could get. Right, people moved as far away as Edison because Edison would, if you didn't pay Edison for the use of a camera, if you just made a bootleg camera that wasn't, patented by Edison, Edison was apparently famous for sending thugs around to go and smash your cameras and beat you up. So that's why they moved Hollywood as far away as Edison as possible, so that it wasn't worth their effort to. So like I said, he gets a lot of hate. Some of it deserves, some of it not. Okay, so what Edison did is he figured out that you could put granules behind the vibrating disc of the telephone. So the idea is the telephone is that what you could do is, rather than having, in order to change the electricity that flows through a wire, what you can do is you can have a variable resistor that just imagine, let's start with this. If you have a resistor that when you step on it, it conducts more electricity than if you don't step on it. Yeah, that makes sense? Yep. So if you step on carbon, it conducts better than if you don't step on carbon. Right? So if you had a carbon pad, it will conduct electricity better if you're standing on it than if you're not standing on it. Now, replace, instead of a pad that you stand on, with a small disc that you speak into. When you speak into it, and I'm now putting my hand in front of my mouth to say, when I speak into it, you can feel that relative pressure that's pressing on those on that carbon, and that carbon will conduct more electricity when that pressure of your sound waves hits that pressure sensor. That's the general concept of how microphones work, and but the reverse end of how we actually make speakers work is you connect a magnet to the back of a diaphragm, and the electromagnet will generally it pulls. I don't think it ever pushes, but it vibrates that magnet, and it vibrates the magnet, which produces the same. I'm now shaking my hand in front of the microphone. It vibrates the magnet in the same pattern of vibrations that your voice makes. I often like to talk about how, as a teacher, what my job is my job is to create connections between your brain cells, between your neurons. And the tool that I don't use a hammer or a scalpel. I use my voice box, my larynx. I shake it, and it shakes the air, and that air shakes between you and me, and it changes your neurons, which I think is a kind of fun way to think about my job. Anyway, so this is the idea of how microphones work and how they connect to telephones, because the change in current in the cable is going to be equal to the change in vibration of your voice, and that can be used to shake a diaphragm to make sound. Okay. Granular carbon was improved, and then people found copper wire was superior to iron wire. Who would have thought? I mean, we just take that for granted, right? Okay, so first telephones were connected via an exchange. So let's see if we can draw up a telephone exchange. If you watch a very old movie, right, they'll when they pick up the telephone, they actually just rang a bell, and when they rang the bell, there would be an operator. It was usually women, you can see here, And what they would do is they would connect and say, operator, can you please connect me to 55, well, they actually usually had letters. So, KL is 55. But can you please connect me to KA62? And they'd say, okay. And they'd connect you to KA62 and they would plug in your cable. And so that would be how you'd connect a phone call. Then eventually we had the rotary telephone, right? So what the rotary telephone did is it has a little thing that makes a beep when this wheel goes over over a dot. It makes a little beep. So if it goes over the number 9, it goes over 9 beeps. So it go and then when you dial 5, it go and 2 1 2. So it could tell how many dots. Right, and so there was a device that could hear the number of dots and then make the connection automatically based on the number of dots that you sent when you dialed the telephone. Then they went to touch phones. I don't even know what to type for that. Button telephone. So they replaced it with these phones, and when you type these phones, instead of sending a number of dots, right, instead of saying right, what it did instead was it sent a pulse, so it sent a tone, and that's where you could hear the telephone. You go do 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 do, yeah, because it could hear the tone, and because there was 10 tones or 12 tones, it could tell you, and so you could actually play songs, right? You could play music with a button telephone.
Liebe Zuschauer, hier ist Martin Lüdekohl und meine Großkante.
I'm already excited. What song's that? So that tone might have been the wrong octave.
Ich hätte auch noch eine Zugabe spielen können, wie zum Beispiel Hänschen klein. Bruder Jakob.
Oh. So some of them sound like they're in the wrong octave for the key that song is in, but yeah, you get the idea, right? So okay, yeah, computer exchanges. Okay, what was also interesting is that in early telephones. So my old boss, he told me that his house was the house you needed, right? To when his parents built the house, theirs was the house that they needed to warrant putting the telephone line in, right? You needed to have like 8 houses on the street before they put in a telephone line, and then when you dialed the telephone, everyone had a shared line, so you had to like agree with your neighbors to say, okay, we're gonna pitch in and we're gonna pay for a telephone. And like, okay, deal. And so when you got a telephone call, you would actually, like, the phone would ring and you'd say, hey, I want to talk to Samson, and everyone else was supposed to hang up. But the reality is not everyone did always hang up. So people could, like, because there was nothing better to do, right? And like there was this or a book, right? So if you just sit there and you'd have to cover the bottom, the handset, so that people couldn't hear you breathing into the phone. So I understand that it was supposed to be pretty good. Well, so when I was a kid, though, a lot of houses would still have 2 phones. So if you wanted to listen to, like, your brother was talking to a girl and you wanted to make fun of him later, right? You could, you could listen on the other phone, and he's like, "Luke, get off the phone!" Or, "Mom, I can hear Luke's listening on the phone," right? That sort of thing, right? I don't think that specific example ever came up, but we definitely did used to listen on, like, our brother's phone calls. Just because, again, nothing better to do. We didn't have the internet. Then, these days it's not really such an. Another thing that's worth pointing out is when I was a kid, you only had one phone number, right, in your house, and your internet ran on that same phone number. So every time you wanted to use the internet, this is worth dial-up noise. So if you wanted to get on the internet, you would do this, right? You would go onto Google and you'd type in your password and you'd dial a phone number for your internet connection, right? And so you'd have a specific phone number. You heard the pulses. And this sound was... And that sound was the sound of the internet.
What did you do on the internet back in the day?
That start bit is
Like,
a
what was even
sound.
on the internet?
Yeah, this...
Or like a sound on like iMovie or something. No, it's the
Well, the ding, this one.
this bit.
Yeah, and the bing bing.
Do you guys
Yeah.
still use
Yeah, our
What
fax machine
for?
works sounds like that.
Well, so doctors refuse to give up fax machines.
Yeah,
Right. Oh, I don't know. So the engineering industry, right? I would say definitely in the course of my time at uni, right? It used to be that if you wanted to put in a proposal, right? So if you wanted to win work, right? It could be a $5 million bridge upgrade, right? If you wanted to win that job, you had to send a fax before 5 p.m. on the day that the proposal was due or the tender was due or whatever. And then eventually, over the time I was at uni, the clients just started saying, okay, we're going to email, right? We put it as PDF and email it to me. And that was a big distinction. Okay. Hopefully you got something out of that. This video I'm going to be continuing through Paul Copeland's Engineering Studies, The Definitive Guide, Volume 2. So this is for the HSC or Year 12 Engineering Studies course. And we're looking at Chapter 4, Telecommunications, and we're continuing on from early improvements on the telephone. So I talked before about how, in the last video, that telephones initially had to go through a switch operator, and then from that they were able to use pulse. A pulse could detect how many times the number had been dialed. So and that was how the number that's how they communicated what number you were trying to call. And then we went to tone dialing, which is doot 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 doot. And I talked about how the internet, you could hear these sounds that when you dialed in the number, you could hear the tone. And we looked at people playing songs on telephones. Anyway, so later improvements. We said that originally the binding of... So we said originally that you would only have... you could only send one signal on a line. When you could add multiple signals on a line, what's that called? Starts with an M? Multiplexing, exactly right. Okay, so banding groups of wires into single carriers which were carried on poles or in underground tunnels. Originally 50 pairs would be bundled together. In modern times we send 2,000 pairs. Even so, there's still 56 million kilometers of cables covering lots of kilometers of route. You don't need to remember those numbers. Okay, Postmaster General's Department in London made possible in the 1980s the first public payphones, right? So they were, you know what payphones are. I don't know. Do you know what payphones are? Yes. Okay, great. Just like they're not common, but they are around. I don't think I've used a payphone in 15 years. Maybe I don't know. I struggle to think of one. Yeah, I definitely used to use them when I was a kid. Anyway, maybe when I used to go fishing, we might, because we didn't get reception. But even then, I don't think I would have got a payphone. I think we would have just bought a Telstra SIM card. Okay. Okay. Also, I guess for Whovians, Doctor Who, he lived in a specialty phone box, which was a police call box. Yeah, that's right. Okay. So, you know what? I did definitely use public phones when I traveled through Europe in like 2006. So well, I did say 15 years. It's pretty close. Yeah, I can definitely remember using public phones then. So you used to buy these phone cards, and they would have like $10 worth of credit to call internationally, and that's how you'd call your family and say how you were going. Especially, you know, I had kids at the time. I don't think we took my kids with me. Anyway, thank you. I'm glad you approve. Okay, so most. Okay, this is an interesting line. Most homes in developed countries now contain a private telephone. I don't have a home phone number. I mean, obviously, we have like 5 mobile phones, and there's only 4 people, but we don't have a home phone number anymore. Anyway, yeah, so I no longer have a home phone. Changing the shape of the telephone. Okay, so they used to have dials with finger holes. We talked about this. Some of the numbers had letters. So, you know, if you hear on TV shows that say some might have like KL5, KL is both 5, so that'd be 55. And the idea is that you would use like a country code or a city code. So you might have like, you know, Sydney might be SY, for example. I don't think Sydney used that, but that's the sort of thing they could have done. We now have redial functions. We have things like I called my mum the other day, and I had someone else call, and I saw call waiting show up. I remember vividly in the 90s when we got our first phone that had call waiting. And, you know, that being this thing. Whereas now I almost never put a phone on hold, a call on hold. I just say to the person, hey, look, hang up. I'll give you a call back in 2 minutes once the other one's resolved. Because no one wants to be put on hold. But in the past, you didn't have unlimited phone calls, so that was a bigger issue. Okay, the history of the telephone in Australia. Okay, Melbourne was the first city to have phones because of the money coming in from the gold rush. Within 5 years, telegraph phones in 1850 rather than telephones. That makes perfect sense. Okay, eventually telegraph was extended out to South Australia and Queensland, New South Wales. And then, excuse me. The first attempt to run a underwater cable to Tasmania was unsuccessful, but it took 10 years before it was finally connected. Okay. Then there was a link with Indonesia, and then Europe, because the links, you know, we were then able to connect to the links that were already in Indonesia to Europe. The coming of the telephone. Okay, so telephones were private companies. So there were 2 in Sydney in 1881. Oh, sorry, 1 private, 1 government. Both state governments decided to buy those phone lines, right? So they became privatized. They became, what do they call it when they nationalized? But in this case, it wasn't nationalized. It was because that means it's a nation. But yeah, statusized, acquired by the state. Okay. It would have been better through a carbon fiber tube. Okay. Okay, by 1905 we started to get radio telegraph. And by 1911, ships could contact through radio telegraph. From the 1960s, with space travel, right? So big jump in that 60 years in technology, right? Through space race, satellites, that sort of stuff. Radio. Okay, so the guy who's credited with the radio is this guy called Marconi. He's an Italian. I think he was working at an English patent office, but you know the Italians claim him. That's why he put the Marconi Club, which is the Italian club out west. It's where they hold the accordion competitions. Marconi drew on the work of Maxwell and Hertz. Yep, all good. Okay, neither of these men could use their knowledge, but so Marconi tried to sell it in England, but they were too slow, so he sold it to private companies. Lloyd's of London, the insurance agent, they were the people who picked up on it. Okay. Okay. So Marconi worked out a way that we could send waves of different length, and that we could this way different wavelengths are allotted to each transmitter. Today, when we turn on the dial to our radio, we are selecting the wave of the station we want. Okay, one of the most important radio services in the early years was carriage telegrams. Marconi set up a service across the Atlantic using stations in Ireland and Canada. Okay, the first voice radio, first human voice broadcast by radio was Reginald Fessenden in 1906. So that was the first voice radio transmission. Okay, Morse stayed the norm until the interwar period. Okay, with ship owners being made. Okay, so biggest customers were ships. The example people like to talk about is that everyone who survived on the Titanic, they're credited with the radio as being the thing that saved them. Okay, this would if the radio operator of the nearest ship had not been at his post. Okay, citizen band radio, better known as CB. Okay, so in some cities, private citizens could use mobile phones, which they could call long distances. The system. Okay, where do we tend to use CB radios? Where do we think of that? Truckers is exactly the right answer. If anyone's ever seen the movie Contact, right at the start, she has, I guess, a ham radio that she uses to contact people several states away. But you can get a private CB license. You don't have to be a trucker. But the idea is that before widespread the widespread network coverage for mobile phones, truck drivers could be stuck in the middle of nowhere with perishable goods, or losing time is as bigger worry as anything else, right? For a truck to be an hour late in its delivery is going to be a big impact on everyone in that supply chain. Okay, entertainment radio. Okay, so in 1920, Pittsburgh, Pennsylvania, which is the only thing I can think of Pittsburgh is the movie Groundhog Day. The very start, he's from Pittsburgh, and that he goes to to do a story on the groundhog. Okay, Marconi himself helped to set up the BBC in London, which was eventually publicly funded, which we've talked before about why English comedy is different to American comedy, because they set up smaller amounts because it's publicly funded. We have the ABC. The ABC gets a lot less funding than the BBC does. I think they get 5 or 10%, 5 or 10 more, 5 or 10 times the amount of funding. Okay, that's a claim. I'm going to say on this video that's a unfounded claim. That's just my intuition, and from what I've got from people, Pom's telling me that our TV is terrible. But someone can check that out and let me know. Won't affect people listening to this video, but Scotty and the Ninjas, I have seen Prank Patrol. Okay, but your average Pom doesn't seem to be impressed by Scotty and the Ninjas. Okay.
They had it as well.
They did. Was it ours? No, they had.
First, then UK, then Australia.
There you go. But I mean, how could Scotty be in all those places at once? Yeah. Okay. Sacre bleu. Mon Dieu, c'est un ninja. Okay. Okay, I'm gonna pause. Okay. In the 60s, a wireless was an ornate cabinet that was the centerpiece of many large homes, sort of like a TV now. Okay. So families would sit around and listen to, there would be radio serials, like plays, that were just audio, but they were, so instead of having TV shows, you'd have audio plays. And I think there's still a tradition of comedy radio in England because, the BBC. Okay, then this decline was halted by innovative programming, including talkback. and more so by the invention of the transistor. The tiny invention replaced the larger and less efficient thermionic valve. So when we hear about vacuum tubes, that's what we used to use instead of transistors. Okay. The transistor made possible portable battery-operated radio, nicknamed the tranny in Australia. The transistor was also the basis of the car radio in the 1960s. Okay, radio stations now had a new audience, people on the move. Okay, I'm not going to go through those dates, but I will say that I've set for homework for you already that you need to choose 10 of those dates that you think are significant. What's interesting is 2JJ converted to FM and became 2JJJ, and the station promoted and still does youth issues. So anyone who's ever listened to Hack, right? Like I mentioned Wednesday's Hack last week. Last lesson. I don't know if anyone listened to that. Okay. Because I forgot my phone, you see. And that's why, I mean, normally I've grown out of, I'm now nearly 40, so I don't need to hear like youth journalism. But I don't know, I teach kids, so I guess maybe that gives me some reason to justify listening to Hack when I have the chance. But I was leaving late from work and I didn't have my phone, which is like, a lose-lose situation. Like, I guess I'll be listening to Hack on the drive home. Okay, but it was an interesting one. And one that I think you guys could benefit from. Okay. So, the effect of people's lives. Right, in Australia we talk often about the tyranny of distance. So I posted today on Facebook someone was saying, I'm a aerospace student, engineering student, and I think that Elon Musk ain't all that and a bag of potato chips. And so some different people tried to convince this person that, maybe some of these things that this person had complained about with Elon Musk actually, weren't as valid criticisms as you might think. The best one of these was someone saying, Elon Musk and Starlink brought internet to my home. Before Elon Musk and Starlink, it took me 10 minutes to download an email or to check my email, and it took, I could only watch Netflix at 1 a.m. So, as far as I'm concerned, Elon Musk has bought himself a lifetime of passes from me. He can do whatever he wants because he gave me the internet. And, this is what the tyranny of distance means. That I tell you, I have been in the country, and when I built my house, there was no internet. There was just you just had to accept there was just no internet. There was a city thing. The city people, they got the internet. You want to watch a TV show on Netflix? No, you couldn't do it. Just didn't exist. Right? It was like my friend who grew up without Channel 10. Right? I mean, these days, you wouldn't even care. None of you would care. Not one of you would care if I said you're never watching Channel 10 again. Right? I know. Right? But at the time, that was 1/4 of the TV. Yeah. Okay. Could not tell you a single show that's on Channel 10 now. There you go. Okay, thank you. Okay. Okay. By the 1980s, almost everyone had a phone. Internet traveled on the telephone. Mobile phones, revolutionary. Some people view this as a bad thing because it invades our privacy. Like, there's this thing where if you said to people in the 90s, hey, you could have all the world's information and the best TV you've ever seen, TV about everything you could possibly think about. You like jazz? Well, I could give you not just one constant jazz channel, not just 24 hours of jazz, but hundreds or thousands of constant jazz channels. How many jazz channels do you think there would be on YouTube and just streaming internet? Thousands? Yeah. Of just dedicated to jazz. You like sea shanties? Well, I've got news for you, right? There's just a constant stream of, okay, well, maybe you might run out of sea shanties eventually, but there's just an infinite amount of content. I remember when I was a kid, right, about your age, saying you cannot possibly watch all of the TV. Even if you watched TV 24 hours a day, you would still have to be choosing between the best 20% of the TV at any given time. Whereas obviously now, that has blown out a billionfold. Like, you could not possibly... You can't watch everything on Netflix. It's impossible to watch everything on Netflix, let alone, the amount of content. I mean, so I'm interested in Magic the Gathering, right? There is more content than I could possibly watch of people playing Magic the Gathering. Right, I don't know if that's true of Mortal Kombat, if there's like streamers who are putting out a heap of Mortal Kombat content. But the point is, it doesn't matter your niche. There is now an infinite amount of content. Okay, moving on. Do people stream Mortal Kombat?
Yeah.
Yeah, there we go. So presumably there's infinite Mortal Kombat content.
Yeah.
Yeah, okay, great. Okay. Look, I just felt the need to say... Oh, okay. The downside of this person you're talking to in the 90s is, well... You're going to have a microphone recording everything you say 24/7. It's going to know when you sleep. And you're going to be tracked by the government. And also, eventually, you won't be allowed to go into a private venue without registering with the government so that the government knows that you were there. And people are like, oh, okay, I do like this infinite TV thing. I'm not so keen on the government tracking. But the thing is, they did it in baby steps and no one really noticed. And then a pandemic kicked that last one down the road. Okay, so... iPhones were revolutionary, right? I think I've told the story before. In 2009, so the iPhone had been around for 2 years. I'm like, I'm not going to go with one of those iPhones. I said that they don't have a removable battery. They have their own specialty port. They don't just use a standard port, and you can't add an SD card. All of those things still remain true to this day, and yet my most recent phone is an iPhone. Why? Well, okay, so in 2009, after making, not long after making those comments, the guy next to who used to sit next to me at work, he heard ding ding, and he's like, so you got one, huh? And I'm like, yes, I got one, because they're revolutionary, they're amazing, I can't believe how good the browser is on this. It was, like Aladdin says, a whole new world of mobile phone use. And now, the reason I've gone back after more than a decade of being an Android user is because I just can't stand the idea of Google listening to me wherever I go. I rather have Apple listening to me everywhere I go, because I trust Apple more than I trust Google. Well, look, so the phone I have now, it has a little yellow dot whenever an app uses my microphone. That gives me a little bit of confidence, Whereas it doesn't have to. No, absolutely. I'm sure the government has a back door that says, no, don't turn on the little yellow dot when we use it. But things like the San Bernardino shooter, which we'll talk about when we get to ethics, is a good example where we can talk about Apple standing up to big governments. Okay, moving on. And like the other side of that, Australia trying to stand up to Google, and we got laughed at. We got clowns, right? Like it's like Facebook as well as Google. Thank you for that correction. Okay. Okay, back to radio. Lloyd's of London is the big name, and then the BBC, the Royal Navy embraced it. Titanic, all of the people who survived that Rose, who wouldn't share a door. Mythbusters do say that she probably couldn't have shared the door. She gets a lot of hate for no good reason. Anyway, but no non-door sharing Rose, she got saved because of the radio. Radio provided lessons to isolated children. If you had to do an engineering report, that is a social benefit you could talk about, that distance education. It also is a big provider of the news. The average person didn't have to pay for a newspaper, right? You didn't have to be able to read. And the big thing, why do governments usually broadcast on AM? Starts with E, yeah. Emergency. So if there's a fire, you can tell people, hey, there's a fire, and you can reach them. Yeah. So the reach is what you said, but emergency. Emergency radio is on AM because you want that reach. Okay, the radio became an important driver for information entertainment. It's essential for aircraft. Okay, that's obvious. Okay. Now, voltage, current, and insulation. At this point, you should know volts, amps, and you should be familiar with resistance, right? Ohm's law. You should know that resistance is measured in ohms. You should, now, how do we test these things? Mostly we test them. Obviously scientists use ammeters and voltmeters, but electricians typically use multimeters, right? Which they have a battery, so a small power source, and they can calculate the current and that's flowing through something, and they can also calculate the resistance of things, the voltage of things. Really important for electricians. Now, we also in the syllabus have to know about signal testing. I've given you some notes on signal testing. I do live next to a guy who works for Telstra, and I've often thought about asking him, but he's a pretty intimidating dude, so we'll see how that goes. I mean, I've been saying that for several years, and I still haven't asked him, but, I do think about it. I nearly asked him the other day, but he was on the phone. So, okay, conductivity. Okay, so how do we measure conductivity? Well, we've got this formula here. So conductivity is the reciprocal of resistivity. You might remember we talked about resistivity in year 11, but again, you might not. You reasonably might not. The SI unit for conductivity is Siemens, not just a phone company, right? It's spelt with an I, Siemens. Yeah. Anyway, and we use the IASC for our standardization of copper. And so we say that pure copper, or the International Annealed Copper Standard, means that pure coppers will have a conductivity of 101%, and silver is 106%, because silver is a little bit better conductivity than the IAS. So we're going to talk about that when just down a couple here. Okay, so yesterday we looked at some telecommunications questions when we learned about different kinds of copper. We learned about pure copper. When we talk about pure copper, we talk about ETP, but that question was mean, and it didn't say electrolytic. It just said tough pitch copper, TP copper. Yeah. Now that is the default, right? That's our 100. That's our what do we say it was? IACS, that's our standard, right? Now, we can have really, really high quality copper. What's that?
OFHC.
Exactly right, OFHC, which is 99.99% pure. It's also worth mentioning that a 0.2 or 1/5% of copper phosphorus is enough to reduce copper's conductivity by 25%. So, how much do we lose conductivity if we have 0.1/5% of phosphorus? We lose 1/4 of its conductivity, right? So tiny impurity of phosphorus, right, totally destroys the conductivity of copper. Yeah, I mean, look, that's not a question that's likely to be an exam, but still worth knowing, right? Okay, so copper beryllium. Why do we like copper beryllium? It can be hardened. Exactly right. It is also non-sparking, right? So I have a picture somewhere of copper beryllium tools, right? And you use copper beryllium tools because if you're on an oil rig, right, and you drop a spanner,
Oxidation is loss, reduction is gain.
Thank you. If you're on a offshore drilling platform, right, and you drop a spanner, it might create a very small spark, but that spark might be enough to blow you up, right? I mean, realistically, it's probably unlikely, right? There's a lot of safety measures, but that is why people use copper beryllium tools. Yep. It is an expensive option, right? It's
Less
not
expensive than blowing up.
This is the key, right? So, but if you're working with like pressure valves, right? So if you're using with boilers and that sort of stuff, or big chemical tanks, that's why they use copper beryllium. So that's a question that we might give, and I did not say that when we said it earlier. So copper beryllium can be hardened, but if I gave you a trial question, Samson, that said, justify the use of copper beryllium tools on for large chemical boilers, or something like that, for chemical plants, you might say...
They're non-sparking.
Exactly what I would like you to hear. They're non-sparking. Okay. Next, we're going to move on to copper cadmium. Why do we use copper cadmium? Okay, it has good wear resistance, but it's suitable for things that have large diameters. For example, right? Yep, big diameter, right? So copper cadmium, I like to remember the D is for diameter. And it's so for overhead wiring. So overhead wiring is how trains get their electricity through something called a pantograph. Do you know what a pantograph is?
Yes.
Yeah, okay. Look, I'll just quickly show. Okay. So trains, they have two wires. This one here that's curved is called the catenary wire, right? And then the one that's level is called the contact wire, and the pantograph touches the contact wire. The idea is that you have these other wires which can be adjusted, so that way you can't really get this straight, right? You'd have to put on way too much tension to get that straight, and even then you're never going to get perfectly straight. So what we do is we accept that we can't get the one straight, we get that one as a curve, and then we set hangers so that we can get the contact wire perfectly straight. And the pantograph touches that wire. And that would be the overhead wiring wire. The catenary wire would be steel, and then we have the messenger wires, dropper wires, yeah. Okay. Okay, here's the different hardness, the relative hardness of these different alloys. Oh, brass we use for like contacts where it's going to be good corrosion resistance. Here we go, brass is here. They are harder and stronger than pure copper while being a relatively good conductor, but it's well below OFHC, or it's well below ETP, right? Let's have a look at its conductivity, right? So brass has 40% IACS, yep. Yep, international anneal copper is 100%, and so OFCH has 101%. Even electrolytic tough pitch as well. Yeah, 101. Okay. Next, we're going to talk about semiconductors. Now, I'm not going to go through semiconductors in too great a detail. What I will say is that semiconductors are made from doped silicon, which means you take silicon and you add small amounts of boron or arsenic or phosphorus. Now, we have covered this in great detail in other locations. The first place I'd say is go and watch the Veritasium video, would be the first place I would start. Okay, I have other videos which talk about the depletion zone in greater detail, but really I don't need to cover that. I think we just need to know that semiconductors exist. They're created from doped silicon. We take silicon, we add small amounts of other elements. Now, what do we use semiconductors for? If we have two layers of semiconductor, an N-type and a P-type, we get a diode. A diode allows the flow of electricity in one direction. An application of diodes is LEDs. LEDs are used in screens and to let you know that things are turned on. We also have xenodiodes. Xenodiodes only allow flow of electricity when the voltage is high, right? This can be useful for voltage regulation. Okay. We've talked about LEDs. We also have laser diodes, which are used for sending signals on optical fibers, right? So it's pretty important. Then we have the transistor. The transistor is a triple layer of semiconductors, and it has two functions. Samson, what is one function? Transistors, two functions, yes?
Amplification.
Amplification and switches. Excellent. Okay. Hey, I'm okay with reading as long as you get an answer. Okay, good. Now, you should know these symbols. You should be able to define these things, right? This is pretty important. Okay, polymers. Obviously, we use polymer casings on cables, right? That's something we're all familiar with. We've all seen a copper wire with a polymer casing, but even optical fiber will still have a polymer casing to prevent corrosion. Okay, they also provide so insulation, shock absorptions, shock resistance. Okay, and they lend. How do you produce them? How do you produce the polymers used? Ejection molding. Okay, telephone casings used to be made out of ABS. These days, the housing for telephones is more often going to be some sort of, it's often glass or aluminium or something like that. You do still sometimes have plastic casings on phones, I guess. I haven't owned a phone that had a plastic casing at some time. Okay, many phones tend to use polycarbonate housing in conjunction with glass face of the touchscreen. A notable exception is the Apple V, which uses anodized series aluminium. So there we go. I think we've talked about those things. Okay, optical fibers. Okay, so how do we send the light beam? Laser diode. Laser diode. Okay, so what do we send the light beam through? 5 letters, starts with a G. Glass. There's 2 layers of glass, right? So we want different levels of purity in the glass, so that way we get what kind of reflection?
Total internal.
Excellent, thank you. That's exactly right. Okay, why do we use? So what are some benefits that we like for optical fiber? Let's say we won't talk about glass. We won't talk about cost.
Small diameter.
Okay, which means that through the conduit we can send
lots of information.
That's exactly right. For the same diameter we can send more information. That's what we could talk about bandwidth. The same diameter pipe or conduit can send more information, a high bandwidth of information. What else? Okay, so the speed of the information, when we think about pipes, we're thinking about flow rate. Bandwidth takes into account the speed, right? So the fact that it's faster, it does send a faster signal. That is 100% true. We also then can have smaller cables, which means we can send more information per diameter.
Less resistance.
Okay, no, don't go with that. Something else. What happens with why do coax cables need boosters?
So attenuation.
Attenuation is exactly what I'm looking at. Optical fiber still has 2 types of attenuation. Where does it have attenuation? First one starts with A, AB, ABS, absorption, right? Some amount of impurity causes the light to get absorbed. So we do have that. And the other one is we have leakage. How do we get leakage? At the joints, right? If the joints aren't perfect, we lose light at where it escapes. Okay, so we have 2 layers. We have total internal reflection. Okay, the other advantage of optical fiber is it's not electric, and because it's not electric, it's not affected by
Water.
Yeah, it looks not affected by water, but if water's getting down, then you probably have problems.
Power surges.
Power surges. Not affected by power surges. What else? We were talking about privacy before.
Oh, yeah.
Oh, people tapping in.
You can't tap in on it. Yep, okay. Doesn't mean that the government doesn't listen to you, they just listen to you in different ways. Okay, so this basic components of an optical fiber system, we have a semiconductor laser transmitter, so a laser diode, right? We send that signal, we send the laser diode signal. We have a photodiode receiver, right? So we have a receiver that can detect that light energy. Yeah, a photodiode receiver that can detect that light energy and send it to the computer. Okay, types and applications. I'm not going to go into too much detail except to say that we don't use multi-mode very often. I've set homework for you to talk about signal mode and graded index. Okay, so single mode fiber is favored for long distance telecommunication. And it suffers the least losses, it has the least attenuation, but it costs a lot to make. When bandwidth is required, we use multi-mode. Okay. Stepped index is the least used, which is what I said. That's what I said already, Copeland. Okay. Analog and digital systems. Okay, so this is where we're going to talk about quantizing. And so when we digitize, there are 2 axes that we need to be able to refer to. The x-axis, it measures time. And what do we call how frequently we measure on the time axis? We're actually down here. What do we call how frequently we measure on the time axis? That rate? The sampling rate. Okay, whereas the more precise our measurements, what do we call that? The quantization level. Okay, we'll go, in terms of binary, I'm just going to finish to say, in terms of binary, I've already given you a lot of notes. You should be able to convert a simple 3-digit number to binary. right? You should be able to do that. That is a question you could get as in a trial. I don't think there's a lot of historical precedent for it for the HSC, but at the bare minimum, you should understand that numbers can be converted to binary. So digital numbers, right? These are base 10 numbers. These are base 10 numbers. They can be converted to base 2 numbers. What's interesting, if you want to waste some time, there's people who suggest that using other systems like base 12 or base 6 or base 60 or base whatever. And with that, I'll leave you for today, and we'll pick up on this next lesson. Okay, so we're picking up on HSC engineering or Year 12 engineering studies, and we're looking at Chapter 4 telecommunications, and we're into the electronics component. And the first thing we need to look at is analog and digital. So on the group chat, you'll definitely have seen a lot of things where I've talked about about binary, which we're going to talk about in a second. Something I've said many times is we live in an analog world. The intensity that comes into the room is an analog feedback. The temperature of the room is analog feedback. All of that stuff we perceive in an analog way. But computers, when we look at a graph or something like that, what we really want to do is we want to try and convert that into a number. And we can call that a digitalization. Now, so digit comes from, having 10 fingers, right? If you have a digital examination, it means an examination that uses your fingers, right? In French, the word for fingers is doigt. So we have 10 fingers, so digital originally meant base 10. Now, digital just means numerical, right? So it means converting to numbers. So what we're going to look at is there is a difference between, we talked yesterday about binary versus digital. So binary means base 2, digital is base 10 typically, right? Or we can call it decimal, right? It's probably a more accurate way of saying base 10. And now digital just means numeric. But there are other bases, right? So time is base 60, right? Days are base 365.25, or actually 0.24 to two significant to 2 decimal places. But there are some other ones. If you look at Jan Misely's YouTube channel, he has base 6 he's a fan of, right? And that's an interesting video, but we're not going to go into now. Now, we've talked about how you can count in binary. We've talked about how if you have light switches, you can send different numbers of signals based on how many switches you have. If you have one switch, you can only send one signal, off or on. If you have 2 switches, you can now actually send 4 messages. The other analogy of this is Game Boy Greens, right? So if you have, what was the Windfish one called? Link's Awakening. So the original version of Link's Awakening was in 4 colors, and it looked like that. So you had 4 colors. So this was 1, this was 2, this was 3, and this was 4, right? So it had 2 bits worth of information. Every pixel was coded in 2 bits worth of information, right? If you have 4 switches, well, now you can send 2, 4, 8, 16 messages. If you have 4 switches, you can send 16 messages, right? Then as you start going up, so 7 bits is enough to code all of the keys on the keyboard, right? And then some, so capitals, lowercase, a few other things. They call them the ASCII keys. And then we start getting to higher and higher rates. So I won't go into too much more detail there, but for fear of being wrong more than anything. But so when we talk about computer systems, they had different amounts of RAM. So I think the original Nintendo had 8 bits of RAM, right? It could store 8 bits of storage, whereas then the Super Nintendo could, I think some of the games were in 16, some of them were 32. Then we had the N64, which was 64 bits. Computers were in 32, except in about, I can't remember, Windows, I want to say, I think Windows XP was the first one to go to 64-bit? Yeah, maybe. And that's why now you have 2 program files on your computer. You have the standard one and you have the 64 one. Okay, Look, you won't be asked any of those sorts of questions, so we're going to move on. But the point is that so here we have an analog signal, which has, all of these things. Whereas ultimately, if we convert things to binary, what we're going to do is we're going to take the number that would be used to represent every position, every amplitude on this curve, and what we would then do is convert that number into ones and zeros. So to do that, look, for me, in my exams, I think you should know how to convert a number like 200 into binary. You should be familiar with that. The likelihood of that being in the HSC is pretty low, right? I don't think there's any historical precedent for that, but for me, I think you should be able to know how to convert the number 200 or the number 600 to binary. There is something called integer overflow, which is interesting, but we're going to move on. Okay, which is like the idea that if you have 2 to the power of 8, you can store up to 255. The reason for that is it's 256, but it actually goes from 0 to 255. So when we store colors, we do 3 lots of base 8. So it's 255, 255, 255. So the actual numbers are huge, right? The range when we talk about a color. So if I look at just say like Ferrari red, okay, so Ferrari red has the specific hex code 255400, yeah, which can be written as a hex code like that. Tiffany's blue has a very specific and copyrighted or trademarked blue, rather, not copyright, trademark. Okay, so how do you convert? I'm going to be very brief here. You can read Copeland's book; it's a good book, but what we're going to do is we're going to take positions of this curve on the x and y graph. The x coordinate it represents time. The y coordinate represents intensity, right? Volume or brightness or temperature, something like that. Now, the more accurate we get with those in the x or the y direction, the more closely our signal is going to represent reality or the input that we've been provided. Now, accuracy on the time scale is called. This is a test. The question. Sampling rate. Accuracy in the y scale is called? Quantization. Yes. Okay. So we call this process digitalization. Okay. So okay. Digital media is less and less important these days, right? So compact discs. And I remember my dad coming back from a conference and telling me that DVDs were going to revolutionize the world. But what these things do is they store information as bumps on a reflective disc, and they can be read by a laser. Those bumps can be read by a laser. Okay, so now we've got modulation and demodulation. This is the crux of the whole telecommunications course. So we're interested in AM, FM, and phase modulation, PM, also known as we might call this digital. Yeah, like time, but the difference is these ones are written with capital letters. Yeah. Okay. Now, before we move on to that, we're going to talk about the concept of multiplexing. Now, the video we watched, the Lightspeed video, it shows the example of multiplexing where it shows someone playing on the xylophone and just effectively says we could consider each of those, each note being a different signal. So what's middle C, concert C? 440,000 hertz? Concert A is 440 hertz or kilohertz?
It's 440 hertz. Yeah.
440 hertz. Okay, everyone was right. I was I don't think in my head I wasn't hearing the zero.
432, which Adam Neely's made a video about. Because the concern, some people like to tune everything down to 8 equals 432.
Interesting. Okay, so just because the microphone probably didn't pick that up, Adam Neely, an often mentioned YouTuber in this class, at the time of recording, he wrote he made a video where he talked about setting it to 442 hertz.
432.
432. There we go. Okay, that makes more sense.
Apparently sounds warmer.
warmer. Okay, the point is that let's say that if you wanted to send all the messages to one person, you might set them on 440 hertz, and you might send the message to another person on 430 hertz, and a message to another person on 400 hertz, and so you could send multiple messages, and as long as you can filter out that specific frequency, you can say, oh, well, this message has come from that person. Now the question is, how close can those ranges be? Well, if we look at radio stations in Sydney, they're about 0.8 million hertz in the FM spectrum. So like, I can think of like the two biggest stations, I think, are like 104.1 and then 104.9, right? So they're owned by the same company, but they're 0.8 megahertz apart, right? So anything closer than that, they start to bleed into each other and they interrupt each other. So they obviously can't be too close together. Okay, so before we get to modulation, I just want to remind you that we're going to come back to that, right? So that's important, but we're going to see that in practice further down the page. Okay, we're interested in how radio waves travel. So radio waves don't bounce off into space. If they're under a certain frequency, they will reflect off the ionosphere of the sky. Okay, so radio waves that, if the radio waves are below 30 megahertz, they will be reflected from the ionosphere, right? So this is why AM is more likely to be reflected, because AM radio is in the kilohertz range, right? Well under 30 megahertz. Whereas we just talked about how most FM radio is in the hundreds of megahertz. Okay. For example, mobile telephone systems use weak low power transmitter, while shipping requires far more powerful transmitters. Okay, that makes sense that if you want the signal to be picked up, we need more powerful signals. Okay, for outer space communication, the frequencies must exceed 30 megahertz for it to travel through the atmosphere. In practice, we typically use gigahertz, things in the gigahertz range. So there was a question that asked in the HSC that we looked at previously that said, what is a typical, what range of the electromagnetic spectrum is used for satellite communication? What was the answer? Does anyone remember? It was gigahertz, but they said they gave a different definition.
Oh, the range. Yeah, we did this.
Beep.
Microwaves.
Microwaves is the answer. But yes, you think about your Wi-Fi router, it's in the 2 to 2.4 gigahertz or 5 gigahertz, whereas satellites can be in the tens of gigahertz. Okay. Amplitude modulation. So now we're going to talk about AM. So what AM does, and the Arctic Monkeys have an album called AM, and their signal from that album called Do I Want to Know features a lot of AM modulation. Okay, so what we do is we add the amplitude. I think AM is the most obvious. If anyone's done waves in physics, you should be familiar with the idea that if I just take the value of this and add it to the value of this, and I take the value of this and add it to the value of this, I get a amplitude modulated wave. Now the fact is that the carrier wave is always much smaller than the signal wave, right? So that way you can just draw the signal wave, but you just color it in with a signal wave, right? And that's what you can see they've done here effectively, is that they've just taken the original wave. We'll look at some better examples, or yeah, I don't want to say better, but we'll look at some different examples soon. Yeah, we'll do it in a second. Okay. They then can be, the process of reverting it to the original signal is, starts with a D. Demodulating is what it's called. Okay, and there's a demodulator as the device. Okay, frequency modulation is a little bit more complicated. It's not as obvious, and what it does is wherever the intensity of the signal is higher, the carrier will become higher frequency and shorter wavelength, and wherever the signal is low, we're going to have spaced out signal. right? And so what we can do is we can tell FM. Now we should talk about the advantages and disadvantages. AM goes a longer range, but it has poorer quality and is more affected by interference. FM sends clearer signal. You can send more information, but it doesn't have the same range. Okay. The last one is phase modulation, which is now we're going to go to, I'm going to pause. Okay, so we're back, and I've gone just to my Google Classroom where I've got some information. So let's, a quick summary. AM suffers from spikes, so electrical spikes, which increase the amplitude and distorts the signal, but they have a long reach. Now the thing is to remember, if there's a surge of electricity that increases the amplitude of the whole signal, well, your radio can't tell that. So it won't be able to, because it's looking for a specific frequency and it's going to remove that carrier frequency. So if it takes out the amplitude, it just won't signal. So instead you just get static, right? FM, if there's a spike, the amplitude can change, but that doesn't distort your signal because all that matters is how close together the waves are. Okay, phase modulation. Now, easier to modulate is a tough thing. You know, like I really should have some sort of qualification there. I'm sure I've read it somewhere, but it's easier with modern technology to use phase modulation, right? It's easier for us. I mean, every one of us in this room has a phase modulator in our pockets in our mobile phone, right? Because we can all pick up Wi-Fi, right? We probably all have at least 2 devices on us to pick up Wi-Fi. Me, I've got this, which is 3, right? And that's only when I'm only carrying 1 mobile phone with me. But on the other hand, none of us are carrying an AM modulator with us, right? Well, okay, maybe some of you have got a little transistor radio in your pocket, you know, so you can listen to the races or something. But the fact is that in the occupation of France by the Nazis in World War II, that the resistance fighters would make their own AM radios out of just equipment that was not readily available, but that they were able to get from hardware stores. Whereas now, that technology is just a very different technology. You know, we could not scrap together if we were in an occupied territory. We probably couldn't scrap together the raw materials to make a phase modulator. Would be my argument. I don't know. I'm saying that on a recording. But when I say easy to modulate, right? If you write easy to modulate, I will give it to you, right? Probably the answer is it's probably cheaper and easier. Cheaper and it can be miniaturized more easily. That's probably a better answer to that. Okay, it's better for moving receivers. Now, we're not talking about FM radio. FM radio, it can pick up the signal over the distances that a car travels. We're talking about things traveling at satellite speeds, right? So satellites, they're moving fast enough that FM radio would actually distort. Remember that FM radio is usually in the megahertz range. You have to be over 30 megahertz to get out of the atmosphere, right? So you don't bounce off the atmosphere. So you need to have very high frequencies, and they're going to be very affected by Doppler effect. This is the sound. The idea is that what that means is that objects moving towards you are going to have their increased frequency, and objects that are moving away from you, I'm trying. All right, I'm trying. They're going to have lower frequencies, and that distorts an FM signal. Phase modulation, unaffected. Okay, you had a question?
Yeah, do they shoot the phase modulation wave like into its path? Like, do they try and shoot it a little bit in front, or is it going so fast that they can kind of just shoot it straight at it?
Okay, the question is, do we aim radio signals in a specific...
everywhere, aren't they?
Okay, so the student has given the answer that I would have given anyway, which is that when we have broadcast towers, my understanding, and I'm not an expert, is that broadcast towers broadly, generally speaking, broadcast in all directions. However, what you can do is have parabolic dishes, and a parabolic dish can mean that it can help you to amplify your signal by collecting signal that you would otherwise not be interested in and bouncing it back in the direction that you want it to go. Because the nature of a parabola is that everything that hits goes out in the same direction, in a parallel direction. Okay, so here's probably the greatest picture I've ever drawn using a mouse. I have amplitude modulation looks like this. It has highs and lows in its amplitude. Phase modulation has close and wide, and frequency. I said the wrong thing. Thank you for catching that. That's one of the big advantages of recording in front of a class. Phase modulation, on the other hand, it has changes of direction. So that the amplitude doesn't change, the frequency doesn't change. What happens is it just turns around and goes back. I was driving to school today, and my daughter was driving, and we came to traffic, and there was like 10 cars backed up. And I'm like, just change direction, go back, go in the other way. We just go around. Okay, so here we can see an AM signal. Can you see how effectively, if this is your carrier wave, that it kind of looks like the AM signal, just it fills in. But when it fills in, the AM signal, right? So the AM signal is, we can imagine what its wavelength is, right? We can see what its wavelength is. It just fills in. Can you see how it's symmetrical?
Yeah, so it never changes frequency.
Never changes frequency, but can you see that it's symmetrical? So our signal looks like this. What this does is it's symmetrical, right? Now, what we want to do to demodulate, which is what a radio does, we talked about demodulation earlier. A radio, right, a radio receiver, or the thing that you have in your car, demodulates the radio. Now, we're not going to go into that in too much detail in this video, and I'll tell you why. And that's because I've decided that's not going to be in the test for our trial, but I might record another video as part 4 when we get to that. So the point is, there is a process of demodulation, which we'll go into in a bit of detail in a second. Okay, so we've seen AM, FM, we can see that where the amplitude is high, it's a tight curve, it's a higher frequency and shorter wavelength. And we can see where the signal is low, we have a longer wavelength and a lower frequency. Okay, now phase, we can see nothing, nothing, up, turn on, nothing, 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 up, turn off. Nothing, 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 up, turn on. Now, another word for saying turn off and turn on is toggle. So nothing, 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 toggle, nothing, 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 toggle, nothing, 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 toggle, nothing, toggle, nothing, toggle. Yep. And so when we send binary signal, that's how we use phase modulation. Okay. So, I have some more details here. I didn't draw this because students have asked, but it gives you an idea of how this will look. Okay, what we are going to go to, I'm going to pause for a second and I'll just get... Okay, so we're back. So we have some questions where we talked about, do we intentionally, when we broadcast a signal, do we just rotate to spherically in every direction? And the answer is broadcast towers typically, but we can use repeaters and transmitters where we are focusing. And I mean, here they're being just drawn as rectangles, but the fact is we do have parabolic dishes which have that function. Again, not my area of expertise, and you're probably not going to question that specific nature, but it's hard to know. It's because it's relatively new, because it's only 10 years old. The 20 years old. The telecommunications content. We don't have the same breadth of examples that we do for things like trusses, where we have 30 years or 40 years of questions. Okay, what we're going to look at is this question from 2019, where it says, okay, look at this diagram, and I want you to tell us what the signal looks at each part of the circuit. If you put an oscilloscope, which shows you what the wave looks like, what would the wave look like at all of these locations? And look, it's a really great question. This is the sample that they give you. So we can see remember how a signal is symmetrical? So that when we take out the first half of the wave, how do we get rid of that bottom half of the wave? How do we get the signal that's only going in the positive direction? I'll give you a clue. It's a semiconductor. What's a semiconductor that only allows flow of electricity in one direction?
I've seen the diode.
Just a regular diode. Yeah, okay, we got there, diode. Okay, excellent. Okay, so once we have our diode, what our diode does is it cuts out the top half of this picture and just gives us that. Then what we need to do is we need to get rid of all of these little wavelengths and just smooth it. When we want to rectify, how do we get a smooth wave when we rectify? Okay, so a rectifier contains multiple components,
including 4 diodes.
Including, well, okay, so that gives you a full wave rectification. But remember, we also have smoothing rectifiers, right? And so they use a capacitor, right? So the capacitor smooths out the rectified signal to produce the demodulated waveform, right? So if we look at this diagram here, the diode cuts out the bottom half, right? And then the capacitor smooths out the signal. Yes?
So is that kind of transferring what you basically call AM back into the signal? I remember seeing the signal like that, and the AM.
Now I asked you earlier, what do we call that when we take it? When we take out the module? Yeah,
So
which
that's
we
what this is.
and that's what a radio does. A radio, you take someone who talks into the microphone, they broadcast as a modulated signal, and then the radio demodulates it. So that way you can convert the inaudible shaking of the air that's all around you, and because that's what the thing about this. There's radio signals all through this room, right? But what the radio does is it demodulates the frequency that you give in any specific frequency, filters out that frequency. Then the diode takes out that symmetrical component, and then the capacitor smooths it out to something you can hear. Yeah. Because even at this point, you still can't hear it because the frequency is too high. So some students in the back of the room have been annoying me, but I haven't said anything, where they've been playing headphones at increasing frequency to hear at what point their human ears can no longer hear that frequency. If they had a dog in the room, the dog would probably be even more upset because the dog can hear higher frequencies, right? But the point is, there's lots of high frequencies in this room that we just can't hear, right? So the frequency is too high for us to hear. So to bring it down to a frequency we can hear, that's what the capacitor does. Okay. Now, I'm going to say here with all of this stuff, I am not a telecommunications expert. I didn't do telecommunications at uni. So a lot of these things, I feel a little out of my comfort zone. This is only through years of teaching it that I've slowly got better and better and more comfortable with the content. But what I will say is that Copeland is a very well-respected voice on the topic. So by all means, read his textbook. I'm sure that nothing that he says in his textbook is wrong, whereas what I say in this video could well be, right? But it's my best understanding, and I've been doing this for a long time. I'm pretty confident I'd get good marks if I was to do any given HSC exam for engineering. Okay. Now, we're not going to go into any more details than that. I think that's sufficient for us. I do have some other links that I'll give you about YouTubers who show you with oscilloscopes what the modulation process looks like. But for the moment, we're just happy to leave it there, right? Because we want to try and get through this. Okay, so in terms of television transmission, I'm not going to go into too much detail, right? I have, when I was cleaning out my garage, I found some notes about how TVs work, how cathode ray TVs work, how microphones work. And, it's stuff that I found interesting, but it's not really the extent of this course. What you should know is that initially people used black and white televisions, and what they did is they took a radio signal, and that radio signal, what it would do is, so cathode rays spit out electrons, right? Those electrons, when they hit phosphorus, the phosphorus glows. So what you do is you have a whole bunch of phosphor dots on your screen, and you set up a cathode ray tube or an electron gun that's going to shoot out electrons, and you just move that gun to fire to travel in a set pattern. Then you turn the gun off and on, depending on if there's supposed to be light there. So let's say that there was supposed to be bands of white light. It's going to go in a horizontal pattern. I'm pretty sure they went horizontally, and it go. I'm going to say the sound of a gun. Da 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 da. Gap for the black bars. Da 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 da. Gap. Da 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 da. And then we just do that for every row. Now then, what we had to have, one gun. Yep.
So very fast.
Traveling at thousands of times per second, right? Wait, a full cycle. So it has to go through the whole screen in 24 frames per second. So it means it has to travel through the whole thing in 24 frames. And then if you had a look at so Australia had PAL, P-A-L, whereas America has NTSC. And so what it would actually do is it would do every second dot and then come back and then fill in the alternate dot. I think that's what PAL did, whereas NTSC, I don't think, I just did it in one go. But yeah, so it had to refresh the whole screen every 24 times a second, right? 24 times a second. But obviously, there are lots of pixels. So I think there was there was obviously more than 720 pixels. I mean, there weren't pixels, but there were phosphor dots. So anyway, I'm outside of my area of expertise, but yes, it was traveling very, very fast. but it was effectively sending an analog signal, because that electricity, the electrical pulse that was being sent to it was an analog signal. So it wasn't like it was coded in by hand by a person or by a computer. Now what we have instead is we have LCDs. But anyway, we'll talk about, first we had black and white. Now, I asked my mum, hey, when you were a little girl, did you ever, did you know what you were missing? And she was like, yes, we were aware what things looked like in color. And we were aware that we were disappointed that things were not in color. But, the thing is, for me, I didn't really feel like, when I was a kid, I didn't feel like I wish things were in HD. I was aware that my Game Boy was black and white and my Super Nintendo was in color, and I wish that my Game Boy was in color. But, I didn't think of it and think, oh man, wouldn't it be great if we had lifelike style graphics that we now have in games like Red Dead Redemption or whatever. Cyberpunk, it's probably too soon to talk about Cyberpunk at the moment. Okay. Is that the bell? No, not yet. Okay. Okay, thanks. Okay, so people are aware that they wanted color TV. So what they had now is they had 3 beams. The system had 3 beams that react on red, blue, and green. Color phosphorus on the front of the CRT. So I don't know if they actually had 3 beams. I think they maybe used mirrors to deflect it so that it would hit the green. So there was a green row of phosphorus, a red row of phosphorus, and a blue row of phosphorus. I thought there was still 1 electron gun, but I thought there were mirrors that sent the signal between 3 different spots. So it would go like 1, 2, 3. So it would do like it would hit the red wavelength that would hit the red phosphorus sheet, and then the blue one, then the green one. The point is, no one matters. This is all old tech, right? So now we have digital technology. So digital technology, you're all aware of the concept of pixels. If you're not aware of the pixels, don't watch the movie with Adam Sandler. That is not what we're looking for. Instead, what we're looking for is analog versus digital. And here, we have binary and we have monitors. So that's where you can learn about how digital technology works using monitors. We've already talked about how every pixel is coded with an 8-bit number, right? 8-bit number gives you 256. 3 lots of them gives you millions of colors, right? So you can be very, very precise with your colors compared to the Game Boy, which only had 2 bits, which could 4 colors. Whereas effectively, we've got 3 lots of 8. So we've got 24 bits, right? 24-bit color compared to 2-bit. For 2 bits, you had 4 colors every pixel, whereas now we have, I think it was actually tens of millions of colors. Okay. Now, digital TV means you either get the signal or you don't get the signal. Another advantage of digital TV is you can have a lot more channels. Now, I remember there being a question on digital TV. It should be in my collection of Facebook questions, but it was poorly received by teachers and students. It said, what are the advantages, aside from picture clarity, what are the advantages of digital TV over analog TV? Right, and generally you don't want to talk about cost of transmission. But the fact is, if you have more channels, you can get more advertising revenue. That's a big feature. Then they had things like you can send more digital information. So you can send things like the TV guide along with the channel. And the fact is that those sorts of things were sometimes available with teletext before digital TV. But yeah, just you can send a lot more bandwidth, which means more channels, but also gives you better picture quality. Products such as Apple TV promote as a product that delivers media content via internet to television. Well, this is probably written before Netflix became a international phenomenon, and now streaming television is a huge part of our entertainment system. Also, it's probably written before Facebook. You know, I mean, I'm sure Justin Bieber was around by the time this book was written, but I mean, I'm using him as an example because he was just some kid singing on YouTube and then became he became a legitimate celebrity, right? And he was a guy who was singing on the YouTube, and then Usher's like, find that kid, give him a contract. So the story goes. But the point is now, I mean, I said in the last recording, if you want to watch sea shanty TV, there is an infinite amount of content. I'm making an assumption, I don't really know, but I mean, I've been assured that there's an infinite amount of Mortal Kombat content, and I can tell you for Magic the Gathering, there is an infinite amount of Magic the Gathering content, and I'm sure that if you were interested in boats or cars, that there's an infinite amount of, I'm seeing some nodding of people assuring me that there is in fact an infinite amount of content, which it's an interesting thing, right? As a kid, I grew up at a time where you could literally, I say to my kids all the time, you don't know what it's like to be bored, right? When we take away their iPad for a week, they're going, like, they're pulling out their hair. I'm like, you don't understand. When I was a kid on holidays, we would sit at home and watch the Home Shopping channel because that was the least bad option of the 5 options or 4 or 5 options. Like, we would sit and watch Bert Newton on TV, right? And people talk about steam mops. And you know what? If you went to your friend's house and you made a joke about a steam mop or about, like, you know, the Buzz Aldrin advertising fitness products, they knew what you meant. Why? Because they had watched the same terrible TV too. This is the concept that you guys, like, I don't think fully appreciate. Okay. Look, in terms of telephones, we've talked before about when you speak into a microphone, so people knew that carbon powder, when you press on it, it conducts electricity more than it doesn't. You put that in front of a microphone, it allows you to vary the amount of electricity that goes to a device, right? That's how a microphone works. A speaker, on the other hand, you have a magnet that's attached to a diaphragm, so like a paper cone, and you shake that paper cone by electrifying the magnet, right? The magnet gets pulled closer or further away. That's the general principle, but these days we have digital options that do a lot of these things very, very well. And obviously the speaker in your phone is using, you know, miniaturized technology that's far more complicated and beyond my understanding. I don't even know what that means, but yeah, he said condenser mic. I do actually have a video on condenser mics, but you know, I'm not focusing on that. Okay, so what we're going to talk about here is with mobile phones. I have a set of activities on Google Classroom on mobile phones. The problem is it's very hard for me. There we go. I just kept hearing that bell, and that's it. Look, I'm going to. I'm just going to finish by saying for not for home. Well, it's here. Signal strength, spectrum, infrared, and cell towers are all assigned here with a whole bunch of links and information on those later. Okay, that is where I'm going to pause for